conjugate acids and conjugate bases, and you're like, we don't need to talk about anything. Well, as it turns out, this is a good follow-up to what we've done before. Now, if we take a look at a chemical reaction, you might think, okay, I know how to recognize acids and bases, and I recognize that this guy here is my acid, right? And that this guy here is my base. However, let's look at what happens after the reaction for a second. Well, over here we have our products. And if you look at it, these products actually look kind of like an acid and a base also. In fact, if I ran this thing backwards, H2O plus NaC2H3O2, right? We can see that this guy could be our acid, right? Because it has an H, and then this could receive an H, and so we could get HC2H3O2. In other words, it would just be the same reaction, but backwards, and then plus NaOH. So if we look at it, really we have a base here and an acid here. Right? So we have a base and an acid going to a base and an acid. But it's a little different. It's not just that this is a base and this is a base, or this is an acid and this is an acid. It turns out that one of these acids and one of these bases are related, and the other acid and base are related as well. So let's take a look at how they're related. If I take a look at a reaction like this, like the one above, I had HC2H3O2 as my acid, right? Well, when it broke apart, right, when it gave up its H+, it created this, which was a base. And so I call these two things a conjugate acid and a conjugate base because they're inextricably linked. In other words, that if this base reacted with H+, it would create this acid. If this acid acts like an acid, it creates this base. And so we call them a conjugate acid-base pair. And conjugate actually comes from the Latin for being married, right? And so effectively, this acid and base are like a married couple, right? They can't exist without each other. And the other acid-base pair is also a conjugate acid-base pair. In this case, it was OH minus and H2O, right? And so when we look at our reaction, if we look back at our reaction, one way of looking at it is to simply say we have two acids and bases, right? So let's look at it slightly differently. Let's color code this boy. And so here was our original acid. And here is its conjugate base, right? And so this is a conjugate acid-base pair. But I also have this base and this acid. And this is a second conjugate acid-base pair. Notice that one of the pairs is base going to acid, the other is acid going to base. So every acid-base reaction involves two conjugate acid-base pairs. The acid of one pair is reacting with the base of the other pair to make their two conjugates. Okay. Now, why do we care about conjugates outside of just keeping track of what's going on in a reaction? Well, it turns out that it tells us something about the relative strength of these acids and bases. So, an acid that gives up H+ really easily is a strong acid. Okay, so this is why we care. Let's go over here, right? If we had a strong acid, it would give up H+ really easily. Okay, the way it can give up H+ really easily. So this thing here must be our strong acid. Strong acid, right? Now, it doesn't look like a strong acid necessarily. I wrote H neutral. That's a little weird to say. Why is it H neutral? Well, it gives up that H+ really easily, and I know that this is neutral because this has no attraction to H+. Okay? That's why it can separate completely. If it has no attraction, right, the H plus completely breaks away. It turns out the opposite of attraction is not repulsion. The opposite of attraction is indifference, right? It sounds like we've been talking about dating or something, but no. In this case, we're talking about acid-base strength. So if this ion is indifferent to H plus, then it separates 100%. We have a strong acid, okay? However, if, right, this ion has a weak attraction to H plus, right? Attraction, easy for me to write. Did I do that again? I did. Let's try this. Whoop. There we go. Let's actually rewrite this just a little bit better so it's neater. Has a weak attraction to H plus, right? That means it's a weak base, but it also means that it's going to partially go back this direction, and we'll have a weak acid partially dissociating to H plus and weak base, and we'll have a weak base partially bonding to H plus to make our weak acid. And so since it has a weak attraction, its conjugate is also a weak acid, right? So our weak base and weak acid are conjugates. A neutral ion and a strong acid are conjugates. And as it turns out, a strong base is one that never separates from an H plus, right? It just hangs onto it for dear life. And since it's inseparable, we consider this overall product to be neutral, right? It doesn't give up any H pluses, right? So what you're going to see is that when we look at conjugates, if I know I have a strong base, I know that its conjugate acid is essentially a neutral ion. I know that if I have a weak acid or a weak base, its conjugate is also going to be weak. And if I have a strong acid, its conjugate will be neutral. So it gives me twice as much information about what I'm going to find in solution to know what the conjugates are. Okay. Let's take a look at some practice kind of quickly, right? And the thing you'll need to remember are these two things. To find the conjugate base, simply take away an H plus. To find the conjugate acid, simply add an H plus. So if I'm looking for an acid, I'm going to be adding an H plus. So plus H plus ion plus a proton, right? So I get HCN. Notice that the charge is 0 because I have a plus here and a minus here, and plus plus minus adds to 0. However, if I had CO3 2 minus and I add an H plus, then I would end up with HCO3 1 minus, because again 2 minus plus plus 1 gives me a minus 1. Now if I wanted to go the other direction, if I wanted to find a conjugate base, then I would simply take away an H plus. So that means one way of doing it is to simply draw an arrow over here and say that it creates Br minus plus the H plus they gave away. Oops. Right, plus the H plus they gave away. So our conjugate base is Br minus, right? If I have H2SO3, it has 2 H's, but I only need to give away one of them, right? Acids and bases react one proton at a time. So I would end up with HSO3 with a negative charge because I lost my positive charge. And the reason it works this way is that I have an H plus that I've given away, right? Now you don't have to write the H plus, but you have to subtract the H plus. So one way of doing this is to simply write two products and show that when it gives up an H plus, it creates that conjugate base. If we look at other practice problems, you can see that over here we are doing the same thing that we just did in the practice problems. We're simply writing conjugate acids, conjugate bases. So if I'm writing a conjugate base, I'm losing H plus. And again, it just helps to know the definition. So this would be Cl minus. Here, if I'm making a conjugate acid, I'm gaining H plus, right? because in order to make an acid, I have to add an H plus to it. So I would get HCO3 minus. Okay. Let's see, what else do we have here? Identify the acid and the reactant in the compound or in the ion that is its conjugate base. Well, here's our H plus donor, right? Has H plus. And then over here, missing H plus, right? So that means that HC2H3O2 is our acid, and C2H3O2 minus is the base, right? Or rather, these are conjugates. Right? And so these are our two conjugates for this our conjugate acid and conjugate base for this reaction. Right? In this compound, I'm looking for a base, and so I'm looking for an H plus receiver. Well, over here is our guy that's taking the H plus because it becomes water. And so here's without, right? Without H plus and with H plus. So here's our process. It's receiving an H plus. So OH minus and H2O, our base and acid. And these are our conjugates, right? Now, obviously, the other pair is also a conjugate, but it's a conjugate pair, but it's in the other direction. So HClO would be an acid, and ClO minus would be its conjugate base. Right? So yay us. What else do we have here? Oh yes, we need to identify strength. Now strength is a little weird because sometimes you want to go systematically left to right, but a lot of times you want to just sort of identify its partner first. So if I know HF is the acid, I know F minus is the conjugate base. I happen to know that HF is not, right? That's not strong, right? If it's not strong, then it's weak. And if it's weak, F minus is also weak because the conjugates of weak are also weak. That means that if I put F minus into water, it should raise the pH, but not a lot. If I put HF in water, it should lower the pH, but not a lot, right? If I'm looking for HBr, I know that this one is strong, right? So I know that strength. I also know its conjugate is Br minus, right? So this guy is strong. It's on our list of strong acids. Well, that means that Br minus must be neutral. And that's why KBr, it can be a major component of seawater, or NABr can be a major component of seawater, and you can go swimming in it without worrying about it chewing away your skin, because Br minus is a neutral ion. Now, if I look at water, I know that it is neutral, right? If I know it's neutral, I know the strength of its conjugate as well, and you can write its conjugate as well. So take an H plus away, and you get its conjugate, and I know that this conjugate is going to be the opposite of neutral, and you can figure it out, maybe possibly by looking at the notes, who knows. Now, if I play this game in reverse, when I look at Cl minus, right, I'm looking for its strength, right? Well, I don't know much about Cl minus necessarily, but I do know that its conjugate acid is HCl, right? And HCl is on our list of strong acids, right? It's on the list, right? Well, if that one's strong, its conjugate must be neutral. And that's, again, why you can eat table salt, which is NaCl, without worrying about it chewing away your throat, because NaCl is neutral. In solution, it does not change the pH of the solution, right? Now, if I have OH minus, I might not know what its strength is, right? But I do know that H2O is its conjugate acid, and H2O is neutral, and that will tell me the strength of OH minus. Similarly, PO3 minus has a conjugate that's HPO3 minus, and I know that HPO3 minus is not one of our strong acids, So this must be a weak acid. If that's a weak acid, this must be a weak base, because weaks are always conjugate of weaks. Anyway, this is what we're doing with conjugates. It tells us a lot about the strength, and so I know, for example, that PO3 3-, if it's a weak base, would raise the pH just a little bit. And relative to PO3 3-, HPO3 2- is a weak acid, and so it would lower the pH a little bit from whatever PO3 3- did. Okay, so yay us. Well, let's stop there.